Hi friend, welcome all to my educational channel Math A to Z. In this series of lecture, we are going to discuss all about Wronskian. That is, the definition of Wronskian, some properties of Wronskian, and some uses of Wronskian. And this is the first lecture of the Wronskian series. Now, what is the definition of Wronskian? For defining Wronskian, we let y1x, y2x to ynx are n function of x. Then we denote Wronskian by the capital W as capital W of x or Wronskian of y1, y2 to yn. And we define Wronskian W of x as W of x equal to determinant y1 of x, y2 of x to yn of x, and the second row is y1 dash x, y2 dash x to yn dash x, and similarly the last row is y1 n minus 1x, y2 n minus 1x to yn n minus 1x, where yn minus 1, this means the n times derivative of the function, and this is the Wronskian of y1, y2, yn, and this is the definition of Wronskian. Before going to the main property of Wronskian, we state here an important theorem about existence and uniqueness of second order linear ordinary differential equation, which state that this is second order linear ordinary differential equation. a0x d2y by dx2 plus a1x dy dx plus a2x into y equal to r of x. This is 1. Here a0x, a1x and a2x and r of x are all continuous functions in an interval a, and must be a0x not equal to 0 for all x belongs to a. Then let C1 and C2 be any two arbitrary real number and x0 be any point in the interval AB. Then there exists an unique solution y of x, unique solution of 1 y of x of 1 satisfying y of x 0 equal to C1 and y dash x0 equal to C2 for any two arbitrary real numbers C1 and C2, and y of x must be defined over A. Okay, this is the existence and uniqueness theorem of second order linear ordinary differential equation. Now we get an important deduction from this theorem, and the deduction is if we get a solution of 1, that is y of x of 1 satisfying y of x0 equal to 0 and y dash x0 equal to 0 for some x0 belongs to AB. Then the solution y of x must be identically zero. Identically zero on AB. Okay? Because from this theorem we know that the solution y of x is unique. Y of x is unique. And since y of x0 equal to 0 and y dash x0 equal to 0, that is both the constants are 0, okay, and x0 be any point in AB. So we say that because the uniqueness of the solution y of x in A comma B must be identically 0. Okay, this result is very important and very useful for the further properties of Wronskian. First theorem on Wronskian is a0x d2y by dx2 plus a1x dy dx plus a2x into y equal to 0. This is second order linear homogeneous ordinary differential equation, where a0x not equal to 0 for all x not belongs to AB. Let y1x and y2x are two solutions of 1 which are linearly dependent. If and only the Wronskian is identically 0. That is, the solution are linearly dependent if and only Wronskian are identically 0. Now we go to the proof of this theorem. At first, we take the solution y1x and y2x are linearly dependent. So we must have C1 and C2 are arbitrary constant, not all 0, not both 0. Such that C1 y1x plus C2 y2x equal to 0, right, for all x belongs to AB. Now differentiating both sides, we get C1 y1 dash x plus C2 y2 dash x equal to 0 for all x belongs to AB. And this is a system of two homogeneous equations, and it has non-zero solution because C1, C2 not both 0. So by the property of system of homogeneous equation, we must have determinant y1x, y2x, y1 dash x, y2 dash x is equal to 0, and this is the Wronskian. From the definition we see that this is the Wronskian. So we say that if the solution are linearly dependent, so the Wronskian is 0 for all x belongs to AB. This is the first part. To prove the sufficient part of this theorem, we here let the Wronskian is identically 0. That is, Wronskian of x equal to 0 for all x belongs to open AB. So for any x0 belongs to open AB, we must have Wronskian of x0 equal to 0. And from the definition of Wronskian, we have y1 x0, y2 x0, y1 dash x0, y2 dash x0 equal to 0. And from this condition, determinant 0, we get two constant k1 and k2, two real constant k1 and k2, such that and must be k1 and k2 not both 0, such that y1 x0 into k1 plus y2 x0 into k2 equal to 0, and y1 dash x0 into k1 plus y2 dash x0 into k2 equal to 0. Right? Now we let y of x be a function of x, which is k1 into y1x and plus k2 into y2x, and differentiating we get y1 dash x is equal to k1 into y1 dash x plus k2 into y2 dash x. By putting x equal to x0, we get y of x0 equal to k1 y1 dash x0 plus k2 y2 dash x0. This is equal to 0 because this relation is given. Similarly, we get y dash x0 is equal to 0. So we get y of x equal to k1 into y1x and plus k2 into y2x, such that y of x0 equal to 0 and y dash x0 equal to 0. And we know that this is the solution of 1. So we must have, since y of x0 equal to 0 and y dash x0 equal to 0, so we must have y of x equal to 0 for all x belongs to A. Right? And since y of x equal to 0 for all x belongs to AB, imply k1 into y1x plus k2 into y2x equal to 0 for all x belongs to AB. Here k1 and k2 are not both 0 from the assumption of k1 and k2. So we say that the solution y1x and y2x, this is the linear combination of y1x and y2x, and the result is 0, but k1 and k2 are not both 0 together. So we say that y1x and y2x must be linearly dependent. And this is the proof that if the Wronskian is identically 0, then must be the solution are linearly dependent. Okay? And this theorem can also be stated as, if the solution of 1 which are linearly independent, then the Wronskian is not equal to 0 in AB. By using the above theorem, that is the theorem of linearly dependent, we prove this theorem very easily. First, we let y1x and y2x are linearly independent solution of 1. And if the Wronskian of x is equal to 0, then by the above theorem we say that the solution must be linearly dependent. So this is not true. So we can say that the Wronskian of x must be not equal to 0 for all x belongs to AB. Right? and in the sufficient part we let the Wronskian of x not equal to 0, that is identically not 0. So there exists x0 belongs to AB such that Wronskian of x0 not equal to 0, and since Wronskian of x0 not equal to 0, so we say that the solution y1x and y2x must not be linearly dependent, because we know that if the solution are linearly dependent, then Wronskian of x0, Wronskian w of x0 must be equal to 0. So we say that Wronskian of x0 not equal to 0 imply y1 of x and y2 of x are linearly independent. Okay, and this is very important property of Wronskian. That is, if the solution are dependent, then the Wronskian is equal to 0, and the Wronskian is not equal to 0, then the solution must be linearly independent. And this is the end of this lecture. And coming soon together with second class of Wronskian.